This talks about soil erosion, which is a key subject. I think we all have issues with soil erosion. Mostly people see erosion and that triggers rehabilitation to some extent. So mines are more affected, but it also occurs in farming areas. So yeah, let's get into it. And because we have some time, I'd like to have a discussion. If you have a question, please feel free to ask it. So as an introduction, soil erosion is a natural process that will affect all landforms. So no landform is not susceptible to erosion. It will occur. It's whenever there's an angle, or there's rainfall, or even a wind blowing, erosion will happen. So there's no way of getting past that. It's going to happen. We just have to manage to what extent it's going to happen. So in the South African landscape or context, water and wind erosion dominates. So based on our climate, rainfall, our wind speeds, etc., these are what we experience. So wind and water isn't the only mechanisms of erosion. There are glaciers erode fairly significantly. We don't have that issue. We also have gravitation that can cause erosion, which we also do experience in South Africa, but based on the soil management principles, we're going to focus on wind and water erosion, which is what most of us have problems with. So what we're going to do in this presentation is follow a modeling approach. So looking at the methods that we use to model erosion, we can actually predict or estimate or prevent erosion based off of the factors that we use to determine how much erosion will occur. So we're going to look at erosion modeling, the factors associated or used for erosion modeling, and how we manage those factors from day to day. So the principles used during erosion modeling aids in the stabilization of constructed landscapes and the sustainable land use of those landscapes after closure has occurred. So let's start off with water erosion. So water erosion has a number of soil loss equations associated with that, which is all dependent on certain aspects that's the focus of that model. So the most commonly used soil loss equation is the universal soil loss equation, and there's a lot of variants of this equation, which includes the revised universal soil loss equation, the modified universal soil loss equation, which begs the question, if it's revised and modified, is it still universal? So, but in any case. Then next is the web model, which is more analysis or experimentally based. So there's a lot of experimental design associated with the web model, but essentially it gives you similar outputs as the modified or revised or universal soil loss equation. So in its simplest form, the universal soil loss equation is the amount of erosion, either in tonnage per hectares, tonnage per annum per millimeters, or tonnage per hour per millimeters, etc. So your erosion equals the amount or intensity of rainfall. And this amount or intensity of rainfall, depending on what you're trying to model, determines which equation you're going to use. Your soil erodibility, your slope length and angle, management factors, and your cover factors. So we're going to look at each of these factors and how they influence erosion. So your amount and intensity of rainfall determines which model you're going to use in your erosion equation. So high intensity events, thunderstorms for example, are more erosive than low intensity longer duration events, which makes sense, right? If you have a massive amount of water falling at a small duration of time, that means you've got more volume, less time for that volume of water to infiltrate into your soil, which means you have higher surface runoff rates. So surface runoff and all factors that increase surface runoff needs to be looked at when modeling water erosion. So your annual loss, if you want to quantify your annual loss of soil, you need to look at your annual rainfall. But this disregards your intensity of individual rainfall events, but can be useful for long-term erosion prediction. So if you were to look at closure for a site, and you want to know how much material am I going to lose, and how often do I have to come back and fix the material that's been eroded, place it back onto your slopes or on your beach areas, then annual losses is the way to go. Of course, your high intensity events like your 1 in 1,000 rainfall events, 1 in 10,000, etc., those events can be modeled and can give you indications of what structures you need to put in place to prevent those rainfall events from having exacerbated effects on your site or on your landforms that you've designed. So modeling these events is useful towards construction of slopes and constructed landforms. So your soil erodibility factor, that is usually equated using your infiltration rate, your hydraulic conductivity. So that is how fast water firstly moves from the atmosphere into your soil. And once it's in your soil, how fast does it move to subsoil horizons? So your infiltration rates from atmosphere to your horizons, and then your hydraulic conductivity is from your horizons to subsoil horizons. And this can vary significantly. So usually we measure your saturated or unsaturated hydraulic conductivity. Unsaturated hydraulic conductivity can be an indication of your infiltration rate, although they can differ as well. Then you also need to look at your water storage capacity. So how much water can be retained in your volume of soil. The higher the storage capacity, the more water can be accepted if that soil is dry. But if that water retention is too high and you have subsequent rainfall events, that means you've got decreased volume that can be retained in that soil, which means your capacity will be reached fairly early and you will have surface runoff problems associated with that. Then, of course, it also looks at dispersion. Dispersion, as we saw before, that's when your particles disaggregate upon contact with water. Detachability, which is similar to dispersion, that's how rapidly individual particles detach from the aggregates. Abrasion is a friction between your particles. That is an indication of how easily particles can be transported in your water. If you have a high abrasion rate, that means there's a lot of friction preventing movement of your particles. And then, of course, the mobility of the material by rainfall or runoff. So that's also dependent on your particle size or your texture of your soil. The finer the particle is, the more easily it will be transported through water. If you have coarser particles, they can resist transport. And then, of course, aggregation increases this particle size, the effective particle size, as long as you do not have dispersion or slaking. That aggregate will react as an individual unit. It means more mass, less mobility or potential to become mobile. Some of the other more important properties are your soil texture, particle size distribution, organic matter content, because your organic matter aids in aggregation. It binds your particles together. It keeps them as those structural units and then prevents them from becoming mobile. But conversely, your organic matter has a threshold level as well. If you have too much organic matter, because that organic matter is less dense than water, it can flow on top of the water as well. So it can become mobile. So you need to look at that threshold as well. Structure size and size class. Different structural types have different strengths to which they aggregate. So the stronger that aggregation is, the better it is. Then your slope length and slope angle, which are very important factors, and these are factors we can manage on a site. So we do our landform designs based on what is acceptable slope lengths and slope angles to minimize erosion of a site. So your erosion potential of water is directly proportional to the energy of the surface flow, or the velocity of that surface flow. So as a non-rule, but a basic guideline, if you double the velocity of your surface flow, usually there's about 4 times the potential to transport the material. So that means there's a logarithmic effect. So an increase in velocity means double the increase in potential erodibility of that material, which means you want to slow down surface runoff at all costs. Okay. So steeper slopes increases velocity, which makes sense. You know, gravity pulls water downwards. If you have a steeper slope, the effect of gravity is stronger. Longer slopes increases velocity. If you have a slope with breaks that stop water flow, you know, that will decrease the flow. But if you have a long slope, that means that water has a longer time to accelerate as it flows downwards. So that increases the effective velocity. But when we do erosion modeling, there's a discrepancy between the effects of slope angle and slope length, where slope angle affects velocity more than slope length. And if we look at the equation, this section over here, that's your angle effect with your length effect over there, where steepness is more important than length. So we can manage that within certain ranges. So that's why when a lot of consultants or companies want to do rehabilitation, the consultants goes in and says, do you have money for reshaping your slopes? Steep slopes are a problem. For engineering purposes, we wanted to put as much material on as small a surface as we can, which meant that we figured out what's the angle of repose of the tailings material, build 35-degree angles to maximize the volume on the surface area. Unfortunately, the environment doesn't work that same way. So nowadays we look at the environmental angle of repose, which can be fairly significant or can significantly vary from the actual angle of repose. Just as an example, kimberlite tailings, they generally have very steep slopes, 35 degrees, sometimes even higher than that. However, the environmental angle of repose of kimberlite can be as low as 8 degrees, even less in some cases. So going from 35 degrees to 8 degrees is a significant change, meaning that if you construct at 35 degrees, no matter what you do, you will always have erosion on that site. Because environmentally, it's stable at 8 degrees, and it will try to get to 8 degrees irrespective of how you manage that material. So here's an example that Mr. Piet van Deventer and Johan Hatting did, where they looked at slope length and slope angle. In this case, they kept the slope angle constant and altered the slope length and did erosion modeling on that. The reddish bars, they are no cover, whereas the blue bars have topsoil cover. So if we look at the increase of the red bars, for example, it goes from about 115 tons per hectare per year at 8 meters to about 145 tons per hectare per year with a 4-meter increase in length. So that's a significant tonnage increase. Of course, this is over a period of a year, but still, if you're losing 30 tons of material each year, that's a significant cost to the company to fix that, to take that back to where it belongs. Here's an example where we have a soil with a 12% clay content at different slope angles with a fixed slope length of 1 meter at a rainfall of 26 millimeter per hour. So this is a fairly short duration event, short slope, varying angles. So if we look at the values, your erosion rate at a 1 degree angle, at almost 0% surface runoff, we still get a modicum of erosion. So this is mostly material moving from A horizon to B horizon, or moving from a spot to another spot within this 1 meter without leaving the 1 meter section. So there's still erosion occurring, even though seemingly there's none. But if we go to a 30-degree angle, that erosion rate is 100 times higher than the 1 degree angle. So that's 100 times increase over a 29-degree change in angle, which is fairly significant. So your P factor, your management factor, these factors represent how management of your soil conditions affect erodibility. So this is a factor where we can actually affect how things will happen, whether or not erosion will increase or decrease. Now we manage that. So to equate this factor, we look at ridge height. So if you are doing ridge plowing, how you do your ridge plowing? Do you do it on contour, against contour? What's the height of your ridge? How deep are your ridge? What's your furrow grade? How far they're apart from each other, etc., etc. Are you implementing terracing effects? Are you increasing the number of berms on your slopes to act as a terrace to catch and break the velocity of your runoff? And then what conservation practices are in place? Are there monitoring occurring on the site? Is there someone who can keep an eye on the area to stop erosion events before they become dongas or gullies? You know, if it started as a roll, you have a breakthrough, is there someone there that can fix that breakthrough before it becomes a worse problem? And then probably the most important factor is your cover factor, except for your slope length and slope angle. So your cover factor is also a factor that we can influence through management practices. There's a number of different possible cover options. Something we like to use in South Africa is vegetative covers, usually in combination with topsoiling or a similar store and release cover. Then there's also rock armoring, rock cladding, etc. So why do we prefer vegetative covers? Can someone tell me? You can get more stability from rock armoring or rock cladding, or similar stabilities from rock armoring, rock cladding. Rock armoring can even be more stable than, I don't want to ask you, Christy, you had a class. So why do we like vegetative covers? Aesthetic reasons. Okay, that's probably the least stated but most important factor. We as humans like to look at green slopes instead of gray slopes, right? A lot of studies have proven that people in cities are more depressed than people in rural areas. I agree. So we like green slopes. If you have a tailings facility with a green slope on it, or a tailings facility with a yellow mountain, which is going to get more complaints from your neighbors? The green one or the yellow one? Of course, of course. So we have this fundamental need to put green things where we can see them. We don't like it if it doesn't look natural. And we feel that green slopes are natural. However, they're not necessarily always practicable. So if we look at arid zones, for example, Aggeneys, Springbok, they don't have green slopes even on their natural mountains. Does it make sense to try and give a vegetative cover on that side? They're going to waste water they don't have just to get the grass to establish there. So we need to look at those aspects as well. But the key factor here is that you need to have a cover on a slope. You need something that can break that raindrop impact events, that prevents surface crusting from forming, that can slow down the rate of water flow. So a grass patch will essentially block any surface flow that flows downwards and hits that grassy patch. It will decrease the velocity right there. And that's why we have vegetative covers in areas where it's practicable to do. So when we look at vegetative covers, all vegetative covers aren't made equal. So for erosion modeling, and I know for ecology, this rate of importance isn't the same. But for erosion modeling, contact cover is your most important type of cover. You need to have something that covers your surface, because that surface cover will immediately break raindrop impacts. It will buffer the effect of raindrop impacts. And it will physically block flow, even though it will physically block flow as it prevents contact between the surface flow and the actual soil surface. Once you have a bare surface, irrespective of how well your basal canopy cover is, erosion can occur under those conditions. Then, of course, the second most important is your basal cover. And, of course, this is only for water erosion. This differs for wind erosion. Second most important is basal cover, because basal cover can intercept raindrops at a broad range, even if the actual growth from your basal cover may be shallower. You get a plume. That plume will intercept raindrops and break the energy of that drop. It won't impact the soil surface and create that crusting surface runoff. Whereas canopy cover is less important than basal cover if the canopy cover is higher than 2 meters. So higher than 2 meters means that that raindrop will again gain energy as it falls off of the canopy. And it will have a similar effect as a raindrop on bare soil at that height of 2 meters. If your canopy cover is lower than 2 meters, it can have a greater effect than basal cover on preventing surface runoff. Here's an example of erosion on a 12-degree slope on gold tailings with varying vertical heights between benches. So this is the vertical height between benches. So this is a factor that includes your slope angle and slope length, with poor vegetation, good vegetation, and rock armoring. So I'm not specifically advocating the use of rock armoring through these values. This is actual modeling results, so bear with me. Just as an indication, at a 10-degree vertical height between benches, the erosion rate of a poor vegetated site is similar to good vegetation at 85 meter benches. That's the effect of a good vegetative cover. Of course, it's still a lot lower than rock armoring, but just to give you an indication, if you have a slope, would you want to lose 8 times the material over the same time span? just because of management of your cover. So it makes sense in long-term projections to stabilize slopes. If you're working in the gold mining industry, where tailings facilities are actually a potential resource in the future, each ton you're losing is potential gold recovery lost. So you're protecting a resource in that case. Each ton you're losing is material going down a river stream or impacting a watercourse. So preventing that, even though it costs more, may cost less than not preventing that erosion. And we all know how water affairs can be very strict about impacts on drainage lines. So that's it for water erosion. Any questions so far? Yes, sorry. Yeah, so your recharge is basically a function of your hydraulic connectivity, so your rate of movement from your topsoil to your subsoils. So that will include, or will be included in the erosion modeling. So you need to define hydraulic connectivity, which is an indication of your recharge rate. Yeah. Yeah, so with these examples, all of the factors were held constant, but we changed those management factors, your cover factor, etc. So under these modeling instances, the recharge rate between a vegetative cover and a rock armoring cover was assumed to be the same, although that isn't necessarily the case. You will have thermal variations between vegetative covers and rock armoring. Rock armoring having more extreme temperature variations. That would also mean that your evaporation rate on that rock armoring will be higher. But on your vegetative cover, you will have transpiration that's also included there. So even though you have lower rates of thermal cycling, the actual effect of the vegetation pumping water out can be higher than your rock armoring. So it also depends on plant species and their water usage as well. So the whole reason, or the whole concept of a store and release cover, where you have a topsoil cover with a vegetative cover on top of it, is that you capture water, retain that water, and then release that water back to the atmosphere instead of letting it reach into your tailings material. So preventing acidification and or re-acidification and groundwater impacts. So you want to capture the water actually.
I think the problem with it, with the rock armoring, might also include that if you backfill a coarse material, the draft that you create, the oxidization that you create through the heat soak on the bottom of the slope, that oxidization on the inside will probably create more AMD.
Yeah.
Maybe, perhaps.
Yeah, it can be a driver because you're not losing as much water. So it can increase the rate of acid mine production or acid mine drainage production. However, it's also material dependent. So if you have a chemically aggressive site, typically you won't go for a cover option that will increase that rate of oxidation. Usually you want to have something like a hydraulic brake layer or a diffusion brake layer or something in between to prevent that from occurring. So you can model those covers, but I think Albert van Zyl is going to talk a lot more about cover options and what to use when. So we're going to get to that point in more detail. Thank you. More questions?
In your earlier presentation, you spoke about different types of soils and their level of dispersiveness. I'm trying to combine that presentation with this in terms of alternatives of managing soil erosion. How would you suggest one would manage rain-driven soil erosion in highly dispersive soils?
Okay, that's a good question. How to manage erosion on highly dispersive soils. And that's actually the biggest question for kimberlite rehabilitation. They have that issue. So it's management of your factors that produces or accelerates erosion. So slope angles, how do you manage those slope angles? Can you decrease the slope angle? In most natural cases or situations, you can't change the slope angle. There's a mountain there. You can go break down the mountain, but usually that's not advisable unless you have some economic motive for that. So that brings you back to your other factors. Your management factor, how are you managing the soil? Is there someone there to be a steward of the soil? To take cognizance of all of the impacts that occur on that soil and to fix problems before they become huge dongas. So to fix a roll before it's a donga. And then look at your cover options. Do you have enough cover material to prevent erosion? So good vegetative cover, maintaining that vegetative cover, and preventing things like overgrazing on rural communities, for example, can have more value than trying to add lots of fertilizer or trying to reslope or even bringing in gabions to capture erosion. So I would say teaching people how to manage that soil can be more important than trying to prevent a natural erosion. Okay, there was one more question in front.
You mentioned this concept of an environmental angle of repose.
Yeah.
Now, is there any kind of guidance for the different kind of mine wastes as to what this angle of repose should be? And then is it actually based on the underlying material or on the cover material that you're using?
So that depends on how you want to define it. But yes, there's quite a bit of literature that looked at differences between the angle of repose, which is just a engineering geological feature, or a environmental angle of repose. So there's a lot of literature on different materials. However, that would have to be tested in order to define, because it will be site-specific, depending on what geological units you've mined, what your type mineralogy and grade or particle sizes are of your material, what kind of chemical components are there, is it aggressive or not, do you have slaking, dispersion, etc., etc. Rainfall as well needs to be taken into consideration, so that can actually be tested and equated for you.
Okay, because an angle of repose, a physical angle of repose,
Yeah.
you can measure that in a laboratory.
Yeah.
But in environmental, can you only do that via test work? Is that
It's also a type of measurement, but you need to do more of a modeling approach than you would just the usual dump a load of sand and see what angle it is. So.
and there's no quick fix between a correlation between the two, physical.
I don't think enough measurements have been made to say that there is a calibration factor you can add, because there's so much variation between materials. You know, you need to look at all of the factors to define. Yeah. Okay. Any more questions? Can we move on to wind erosion? So we all know about the Air Quality Act and how important it has become to manage air quality. And a part of that is dust management, and dust suppression, etc. So similarly to water erosion, dust can be modeled. Before you even put up a dust bucket, we can tell you at this wind speed, under these conditions, you will have so much dust blowing in this direction. So that actually to construct or place dust buckets, you need to do wind erosion modeling to define what's your direction, where do you expect the wind to blow, even at what periods of the year you can predict where your dust will be blowing. So to look at wind erosion, we're going to look at some of the mechanics of wind erosion, how it happens. So there's three main processes involved. It's detachment, transport, and deposition. So detachment is when the particles are removed from their place on the soil. It's then transported through wind through three different methods, which we'll see now, and then it's deposited again. So these methods all have their own equations related to them. So moving air detaches particles from the soil. It lifts them up or keeps them on the surface. This then increases the abrasive power. It will hit another particle and either kick up more material or stick where it is, dislodge other soil particles. So depending on the size of the dislodged particle, three modes of wind-induced transportation occurs. These are siltation, suspension, and surface creeping. So wind erosion typically dominates in areas where the rainfall is between 1 and 1,000 millimeters of rain. So that pretty much covers the whole of South Africa. So we have wind erosion risks for the whole of the country. So the mechanisms for wind erosion or transport through wind erosion is your surface creep, which is basically particles moving on the surface. So these particles aren't lifted up, they just kept crawling on the surface. So we do see this in desert areas, usually your larger particles, your gravel, those materials tend to move through creep instead of siltation. Siltation is the process where a particle is lifted from the surface, it kind of makes a bounce, and then through gravity is then deposited again, and this deposit can actually hit other particles off of the surface, and this impact can then kick up more particles, which can then, continue on this process of siltation. And then, of course, you have suspension, where material is blown into the atmosphere. And then because of their particle size, that PM30 and PM10 fractions you need to monitor for dust, they get, or they stay in suspension in the air as water would have stayed in, or clay particles would have stayed in suspension in water, as an example. So these are the three main processes of transportation, and it's dependent on the particle size of the material and whether or not aggregation is present. So a material that disperses will be more prone to suspension transport. If you have sand fractions, they are more susceptible to siltation, whereas your gravel is more susceptible to creep. So the most commonly used wind erosion modeling equation is the WEC equation, which tells you that the predicted soil loss is equal to your soil erodibility factor, your climate factor, soil ridge roughness factor, your width of the field factor. So again, the distance that the air is allowed to move without breaks in that velocity increases the rate that material can be moved. And your vegetation cover factor again. So just to give you an indication, so your erosion is a function of your soil erodibility, which includes your soil properties that are similar to your water erosion properties. So if the material aren't aggregating, they will be more susceptible to erosion. Your soil erodibility in this case also includes your slope. There is a wind amplification effect associated with slopes. So if you have a slope and you have a column of wind moving, that slope will force that volume of air into less of a volume. And the only way that can happen is by increasing the velocity of the wind. So you have a wind amplification effect associated with slopes. Then your wind velocity and turbulence. The stronger or the faster the wind blows, the more material it can carry. The more turbulent the wind blows, the more surface effects can occur. So that turbulence can actually dislodge particles from your surface. However, if you have more turbulence, you have slower average velocity. So there is a threshold to look at there as well. Then your climate. What is your rainfall? Is your rainfall enough to prevent erosion from occurring? The more fluid you have in your soil horizons, especially your air horizons, that water will actually act as a bridge between particles to keep them together, keep them through cohesion and adhesion, keep them from becoming dislodged and being moved as individual particles. So that actually prevents erosion. That's why we use water sprayers, especially on roads, on tailings dams, to prevent dust from being dislodged in those areas. Then your vegetation cover is also added again. This is actually a factor associated with your surface roughness, but in this case, vegetation have more of an effect on decreasing your wind velocity than it did in your water erosion, where it was only a cover factor. In this case, your vegetation can have a dual aspect. So your surface roughness, that's your ridge characteristics, for example, is the turbulence created by the roughness of the surface. The more turbulence there is, the less is the average velocity. However, you may have effects of dislodging particles. And then your width of exposure. So, field erosion controls. Contact cover is the best option for both wind and water erosion, which brings us to grasses. And that's why we use grasses for rehabilitation. It helps for both wind and water erosion. A dense cover is always better than a patchy cover. In this example, you don't expect any erosion from that surface there, right? However, you may expect erosion on one that isn't as densely covered. You need to create obstruction for flow. This obstruction can be created through netting, where you have windbreaks on your key susceptible areas, and always on a slope, that angle between your horizontal and your vertically sloping areas, that is always the area where the most erosion will occur. That's why we don't see angular mountains. They always have a scalloped slope. That wind erosion will attack that angle. And that is where a lot of the dust is generated from tailings facilities, is on that surface. So as the wind is blowing up the hill, once it reaches that angular area, a turbulence is created. And that turbulence will kick material off of the slope. So you need to create obstruction for flow. You don't necessarily want to stop flow. That can be even worse than slowing down the velocity. So you want to slow down the velocity and not stop flow abruptly. That stopping the flow abruptly will blow over all of your constructed material over time. It will create a lot of turbulence in front of the obstruction, and that will degrade your foundations of whatever you use to construct it. Improve infiltration. and improve vegetation establishment. So if you have a surface crust similar to in water erosion, that surface crust will actually increase the velocity of air movement over that material. So any loose particles that is present on that surface crust will more easily or more readily be transported. So you want to decrease that and increase your surface roughness as far as possible. So you need to rip crusts to improve infiltration and water retention. So here's an example of an instrument made to break surface crusting. They can be scaled up to use on tractors. And then treat sodic soils with gypsum, as Dries Bloem said earlier, that sodic soils will accelerate crusting and dispersion, which can increase the smoothness of your surface. So to prevent wind erosion, you need covers, vegetation, mulch, stones, increase surface roughness. Chemical spraying has become very, very popular in the last number of years. And new products are emerging, like polymer sprays, for example, that are very, very good at aggregating particles, irrespective of whether or not they are natural soils or tailings materials. They have a good aggregation effect. Increase water moisture, increase soil moisture, sorry, not water moisture. Increase soil moisture because of that bridging effect of water between your particles that increases your cohesion and prevents transport because you have a larger functional unit of a soil particle. Avoid tillage of dry soils, and this is always important. Don't till dry soils. That's a dust event waiting to happen. Avoid overgrazing. Overgrazing decreases your cover, increases your erodibility. Vegetation height and spacing can be very specific. So we usually use basal cover and canopy cover to reduce wind velocity, whereas you use contact cover to prevent particles from dislodging and becoming mobile. So on your berms and on your top flats, usually on the slope areas, you want something like a Hyperinia hydra that can prevent the wind from continuing on with its high velocity. You want something that decreases the velocity and is strong enough or woody enough not to break when wind events are very high in velocity. Okay, so here's an example of your soil loss ratio. So you have a higher soil loss at lower percentage of covers, which is fairly logical. So usually your functional characteristics of vegetation, these are related to your erosion. So they act as erosion controls, especially stoloniferous plants, creeping grasses. They hug the soil surface and then prevents material from dislodging and being transported either by wind or by water. Vegetation acts as windbreaks. They improve soil structure. They bind material through the rhizosphere. They actually create natural polymers that act as binding materials for your soil. They can function as pollution control. Pollution can actually degrade your soil structure, break down the natural capacity of the soil to resist erosion. So preventing pollution or the effects of pollution can also be a good aspect. Aesthetics we talked about. Vegetation can add shade to a soil. Through the process of giving shade to a soil, that decreases your temperature extremes, which means you buffer the extremes that microorganisms are experiencing in that soil. And by allowing them a better habitat to survive, you increase nutrient cycling in that material, irrespective of natural soil or tailings. And if you have better nutrient cycling associated with better microbial activity, you will have better vegetative cover for a longer period of time. And of course, vegetation can have economic value as associated with the post-closure land use, dependent on what is designed for, and they aid in nutrient cycling. So here's an example. Mr. Piet van Deventer likes to use it. A site with a topsoil cover, a site with no topsoil cover. The difference between the left and the right, if I remember correctly, is about 1 meter of erosion after 8 years of that site remaining as is. It's a significant drop in elevation. That's a lot of tonnage of gold material lost just through natural erosion that could have been stabilized through minimal cover. If I remember correctly, this tailings dam was ameliorated as is. I don't think topsoil was added in this case. So that's just vegetation on tailings. It's not a topsoil cover even. After 8 years, there's a significant difference. Here's another example. I'm not sure about the duration, but again, even though we've got some exotic invaders, they prevented erosion on the site, stabilized the slope. You've got minimal environmental impact resulting from this area compared to, I think I'm too far, compared to on the left side of the image. Thank you. Any questions?
Thanks, Jaco. I think it was very important to point out the difference between wind erosion and water erosion, because to a lot of people, they just treat the two the same.
Yeah.
Over the years at ARC, we've used our land type survey, which has got soil coverage of the whole country, to come up with maps showing susceptibility to wind and water erosion,
Yeah.
and also quantifying some of that tons per hectare, or et cetera, et cetera.
Yeah.
I mean, I'm sure you know what Jay LaRue and colleagues have done over the years.
Yeah.
But maybe other people are not aware of that. That's under natural conditions.
Yeah.
We haven't been involved in the mining and the exploring of things like tailings dams, but that gives you a baseline on a fairly good scale over the country of what to
Yes.
expect under certain conditions.
Definitely.
Been questions asked about sodic soils and obviously the sand grade of your topsoil for the wind erosion and stuff. So we've
Yeah.
got some information. There's reports that were written giving the methodology and how we went about it, and the maps have been produced. Maybe it's time to have those updated at some stage. I mean, I could speak to our colleagues in the GIS department, but those maps are available. There's reports so people can get an idea of what the susceptibility is to wind erosion and water erosion across the country.
Definitely, definitely. It's very valuable baseline information that you can use for planning purposes. Yeah, definitely.
Any other questions or comments?